One, in this AV, we are going to talk about the 8th chapter, that is propagation of sound waves. Now every day we hear different types of sound, maybe coming from different various sources. So we cannot see the sound, but we can feel the sensation, or we can, through our ears, we can hear the sound. So on the basis of this, we define sound as: sound is the form of energy that produces the sensation of hearing in our ears. Now, how is sound produced? To understand that, let's understand this. Here, a boy is holding a rubber string which is fixed at both the ends. Now, he sets the rubber string in vibration. So basically what we have done is, we have provided the mechanical energy to set it in vibration. Now once the vibration starts, what happens is, the mechanical energy through vibration is transferred from one particle to the next neighboring particle, to the next neighboring particle, to the next neighboring particle. Now in this way, the sound which is produced because of the vibration will be heard by us, and we will find that once the vibration of this rubber string stops, then there will be no more sound heard by us. Similarly, here also they have taken a string which is fixed at both the ends, and vibration is made by plucking the string. So once the vibration starts, again it will produce sound, and we can hear the sound as long as the vibration is still there in this string. Once the vibration stops, that means no more sound will be produced. Similarly, if a vibrating tuning fork is brought near a table tennis ball, then we will find that because of the vibration of the tuning fork, the table tennis ball will start going to and fro about its mean position. If you think of a sitar or a guitar, then you will find that there also the vibration. So with these examples, we know that sound is produced because of vibration, or a vibrating body produces sound. Now sound requires a material medium to be transferred from one point to another. This we will understand with this bell jar experiment. We have a bell jar where inside the bell jar we have the electric bell, which is connected to a battery and a key. Once we press the key, then we see that the hammer of the bell starts and goes and gongs the bell. Now that sound is heard. What we do next is, with the help of vacuum pump, we slowly start removing the air which was inside this bell jar, and once the air has been removed from this bell jar, we are no more able to hear the sound. Now what had happened is, initially when there was air inside and this gong was striking against the bell, this produced the vibration which was transferred to the air present around it, which transferred the vibration to the walls of the bell jar, and because of the vibration to the walls of the bell jar, the air around the bell jar also started vibrating, or it was set in vibration, and we could hear the sound. But after the air has been removed from inside the bell jar, then even though the gong is striking the bell, vibration is being produced, but since there are no more air particles, so that vibration is unable to be transferred to the walls of the jar, and which in turn cannot set the vibration to the nearing air molecules, and we are unable to hear the sound. So this experiment tells us that sound requires a material medium to travel. So we say that a material medium is necessary for the propagation of sound from one place to another. Now what are the requirements of the medium? Firstly, the medium should be elastic so that the particle may come back to their initial position after their displacement on either side of the mean position. Next, the medium should have inertia so that the particles may restore the mechanical energy, and finally the medium should be frictionless so that there is no loss of energy in propagation of sound through them. Now, as we have discussed earlier, we know now that sound requires a material medium for its propagation. Therefore, we say that sound cannot travel in vacuum. So, on moon, since there is no medium, therefore we cannot hear the sound produced by others, which is not the case with light. The light does not require any material medium for its propagation, and light can travel or propagate through vacuum as well. When a vibrating body produces sound, it creates a disturbance in the medium, and that disturbance travels through the medium as waves. Let's try to understand how. Now, we take a metal strip which is fixed at one end and the other end is set to free vibration. Now, what will happen is we pull the metal strip on either side and then release it. It will go towards one side, then come back to the mean position, then go on the other side. Now, what is happening? Once this is going towards this side, we have the layer of air which are at a certain distance from each other. Once this metal strip goes this side, it strikes the particles of the air, and those particles, they are compressed at a certain region. Now, this forms the compression because the layers of air are compressed here. So we call this as compression is formed, which is denoted as C. Now this metal strip comes back to its mean position, so they get relaxed, and this energy is passed on to the next particle and the compression moves ahead. So at this level we have the compression. Now this metal strip goes on the other side of the mean position. So these air particles are more relaxed and the compression travels to the next particle. So we see that here the region, this is the region of compression of air particles or air layers. So the compression is formed here. Now here we see that there is more space than the normal. So this region is known as the region of rarefaction, which is represented as capital R. So a compression is a region of high pressure and a rarefaction is a region of low pressure. Now this is how the compression and rarefaction travels from one particle to other. Now you saw that how compression is traveling ahead and how rarefaction is traveling ahead. Now once we have this, we find that this is the direction of wave propagation, and also the particles of the medium are vibrating in this direction to form compression, rarefaction, compression, rarefaction, and the direction of wave motion is also along the same line. So this is known as longitudinal wave. Longitudinal wave is the wave in which the particles of the medium vibrate about their mean position in the direction of propagation of sound. Okay, so here we find that this is the direction of sound propagation and this is the direction of vibration of particles, which is the same. That is why these type of waves are known as longitudinal wave. Thus, sound travels in air in form of longitudinal waves, and longitudinal waves can be produced in solids, liquids and gases as well. What happens is, at compression the density and the pressure of the medium is maximum, while at rarefaction the density and the pressure of the medium will be minimum. Now when the wave was formed in air, we were unable to see the waves, but if the same happens or forms at the surface of water, then it can be seen. For example, this is the surface of water and you drop a piece of stone. Then you can see the wave formation. Now what is happening, that we will try to understand. Now in this case, what is happening is, once you drop a stone on the surface of the water, then the particle of the water started to vibrate in this position, going up and down, up and down. And this is how the particle started vibrating. And this vibration was transferred to the next particle, then to the next particle, then to the next particle, and the previous particle will slowly dissipate the energy or pass on the energy to the next particle, and the waves will just be forwarded, and this side you will find that there are no more waves as the energy has been imparted to the next particle. So what happens is, the particles do not travel, they just pass on the energy. Now in this example, what do we see is, the motion of vibration of particle is along this line, or maybe we can say along x-axis, and the wave motion is along x-axis. Particle is vibrating along y-axis, wave motion is along x-axis. Or we can say that the angle between the vibration of the vibration of the particle and the wave motion is 90 degree. So the wave in which the particles of the medium vibrate about their mean positions in a direction perpendicular to the direction of propagation of wave is known as transverse wave. Now here the transverse wave is comprises of the crest and the trough. The position of maximum upward displacement is the crest, and the position of maximum downward displacement is trough. This crest and trough, they keep on alternating in time at a position. And please remember, or please note, that the transverse waves can only be produced in solids or on the surface of the liquid. They cannot be produced inside liquids or in gases. A wave motion has got two characteristics. Firstly, it is produced by the periodic disturbance at a point in a medium, and secondly, the particles of the medium vibrate about their mean position. They do not leave their position, only the energy gets transferred. Now we understand some terms related to wave motion. For example, the first word is amplitude. Now amplitude is the maximum displacement of the particle of the medium on either side of its mean position. This is the definition, and we have to understand or keep it in our brain that it is denoted by the letter A, and the SI unit is meter. Time period is the time taken by the particle to complete one vibration. Now it is denoted as capital T, and the SI unit is seconds. Frequency is the number of vibrations made by the particle in 1 second. Now this is denoted as Fn or nu, and the SI unit is per seconds or also hertz, which the symbol is capital H and small z. Now the frequency and time period, they are related as F is equal to 1 by T, or we can also write it as T equal to 1 by F. Another very important thing to keep in mind is, the frequency does not depend on the amplitude of vibration or on the nature of the medium in which the wave propagates. The next word is wavelength. Now the distance traveled by the wave in one time period of vibration of the particle of the medium is called the wavelength. It is denoted as lambda. SI unit is meter. Now wavelength depends on the medium in which the wave travels. So in longitudinal wave, the distance between two consecutive compression or consecutive rarefactions is equal to one wavelength. Or in transverse wave, the distance between two consecutive crests or 2 consecutive troughs is equal to the 1 wavelength. Now look at this figure. The maximum displacement from the mean position, this is the maximum displacement, so this is amplitude of the wave, and from 2 consecutive crests, the time taken for the wave from here to here is the time period, or this is also the, if you talk about the length, then this is the wave length from one crest to another crest. That is what we say in the definition, between 2 consecutive crests. It can be 2 consecutive troughs also. Now wave velocity is the distance traveled by the wave in 1 second. It is denoted by the letter V, and the SI unit is meter per second. Now we talk about the relationship between the wavelength, wave velocity and frequency. You know that wavelength is denoted as lambda, wave velocity as V, and frequency as nu or n. So we assume that V is the wave velocity, T is the time period, F is the frequency, and lambda is the wavelength. So wavelength is what? Distance traveled by the wave in one time period. So that distance formula is distance is equal to speed multiplied by time. So our speed is wave velocity or wave speed multiplied by time period. So wave velocity is denoted as V and time period as T. So we have lambda is equal to Vt, or Vt equal to lambda. Now we know that time period and frequency are related as T is equal to 1 by F, or F is equal to 1 by T. So here in this equation, instead of T, we substitute 1 by F. So my equation looks like V multiplied by, instead of T, we are writing 1 by F is equal to lambda. So we cross multiply F with lambda and we get V is equal to F lambda. That is, wave velocity is equal to frequency multiplied by wavelength. This is a very important relation. Please remember that the speed of sound in a medium will depend only on 2 factors. That is, first is the elasticity of the medium, and the next is the density of the medium. Interestingly, the speed of sound is different in different media. In general, we say that the speed of sound is more in solids, less in liquids, and least in gases. You can see that the speed of sound is nearly 5100 meter per second in steel, and when we compare it with air, that is only 330 meter per second. So in steel or in solid, the sound travels faster than it travels in gases. Now there are 4 factors on which the speed of sound depends. First is the density, next one is the temperature, third one is the humidity, and finally we have the direction of wind. Let's see how they affect the speed of sound. Now the first factor, that is density. So please remember that speed of sound is inversely proportional to square root of density. That means if one increases, the other will decrease. More the density, less will be the speed of sound. Here we are talking about the gases. Please do not get confused, because in general the speed of sound is more in solid, but in gases, if the density is more, the sound will travel with a lower speed, or the speed of the sound will be decreased. Next is the effect of temperature. Now the speed of sound in gas increases with the increase in temperature, because it is directly proportional. Velocity of sound or speed of sound is directly proportional to square root of temperature. Then we have effect of humidity. The speed of sound increases with the increase in humidity in air. And finally, the direction of wind. The speed of sound will increase or decrease according to the direction of the wind. If the wind is blowing in the direction of propagation of sound, the speed of the sound will increase, and if the wind is blowing in the opposite direction to the direction of propagation of sound, then the velocity of sound decreases. Then we have three factors which do not affect the speed of sound in gas, and they are pressure, amplitude, and wavelength or frequency. So please note that because of pressure, because of the amplitude of the wave, and because of the frequency or wavelength, the speed of sound in gas remains unaffected. To compare the speed of sound with speed of light, we will find the following 4 points. Firstly, light waves can travel through vacuum, but sound waves cannot travel in vacuum. The speed of light is far greater than the speed of sound in air. Then, the speed of light wave decreases in optically denser medium, but for sound we find that the speed of sound is more in solids. And finally, the light waves are transverse electromagnetic waves, while the sound waves are longitudinal mechanical waves. And because of these differences, we see that when you in thunder and lightning, light is seen much earlier than the sound of thunder is heard, although they were produced at the same time, but we are able to see the light first, then we hear the sound a little later. Now we talk about different frequencies of sound. Now the audible range for human ear, or the audible range of frequency for human ear, is 20 Hz to 20,000 Hz or 20 Hz to 20 kHz. They are the same. This is the range that we are able to hear. Below 20 Hz and above 20,000 Hz or 20 kHz, we are unable to hear the sound. So this range, 20 Hz to 20 kHz or 20 Hz to 20,000 Hz, is known as the audible range for human ear. So the sound of frequencies in the range of 20 Hz to 20,000 Hz or 20 kHz is called the audible range or audible sound, and the sound of frequency less than 20 Hz is known as infrasonic, while the sound of frequency greater than 20,000 Hz or 20 kHz will be known as ultrasound or ultrasonic. We have to remember that human ear is most sensitive in the range of 2000 Hz to 3000 Hz. But we have animals who can produce and hear sounds of frequency below 20 Hz or above 20 kHz or 20,000 Hz. Different animals have different ranges of audible frequencies. Now, the frequency above 20,000 Hz is called the ultrasound or ultrasonic. Now, because of certain properties, it finds various application in our daily lives. It has got two properties. Firstly, it can carry very high energy, and secondly, it travels along a straight line. It doesn't bend. So because of these two properties, we use it in different aspects, and it is very helpful in our life. Ultrasound is used for drilling holes in materials like glass. Then it is also used for cleaning minute objects. Then it is used to detect the defects in metals. In medical field, it is also used in ultrasonography or ultrasound. In echocardiography also, it's used to obtain the image of the heart. Ultrasound is also used in surgery to remove cataract, and in kidneys to break the small stones into fine grains. And finally, in defense also, ultrasound is used in sonar, that is sound navigation and ranging, to find the distance of object underwater. You can watch the Bollywood movie called The Ghazi Attack. There they used, or they have shown, the application of sonar. Now, animals like bats also use ultrasound to detect their prey or to find any obstacle in their path. Now, what is the difference between ultrasonic and supersonic? Ultrasonic is used for the sound frequency above 20,000 Hz, whereas supersonic is used for the objects which can travel with the speed which is greater than the speed of sound. For example, a fighter plane or a jet plane. Thank you.